Review over partial fractions, and we're going to do 4 different cases for completing partial fraction decompositions. So partial fractions are basically taking something like this and rewriting it into a sum of 2 other fractions. So first of all, in this particular case, we have distinct linear factors. So that denominator factors to x minus 3 and x plus 2. So when we do that, we're going to have x plus 7 on the top, x plus 3, x plus 2. And we can set that equal to some numerical value over x plus 3 plus some numerical value over x plus 2. So it's one partial fraction with a constant numerator for each of those linear factors. Now I'm going to multiply both sides by the quantity x minus 3, x plus 2. On the left-hand side, I'll be left with x plus 7 because that will give me my denominator. I'm going to have a times x plus 2 plus b times x minus 3. At this point, I could actually distribute and write a system of equations with 2 variables. But because there are values that'll make the quantity x plus 2 0, like I plug in x is equal to negative 2, I get negative 2 plus 7 on the left-hand side. And on this side, I'm going to get a times negative 2 plus 2. That's 0. So it's going to actually eliminate value. So I'll have 0a minus 5b is equal to 5. So then basically I get negative 5b is equal to 5, so b is negative 1. It's kind of a shortcut instead of actually solving the entire system out. The other value I would pick would be positive 3 because that'll get rid of the parenthesis on the b. Get 10 on the left-hand side equals 5a plus 0b. So 10 is equal to 5a. So a is equal to 2. So this tells me that my partial fraction is going to be 2 over x minus 3 minus 1 over x plus 2. So what we're doing is we're just basically taking a big fraction and splitting it into smaller fractions. The goal in class tomorrow will be to then take integrals afterwards. So here's example number 2. Now in this case, when I look at that denominator, I have x, then x squared plus 2x plus 1. So when I do that, it's going to be x and x plus 1 quantity squared. So instead of having distinct factors, now I have, repeated factors, but we're not going to worry about it. We're just going to have multiple factors. So I'm going to have instead a over x plus b over x plus 1, just like in the last one. Now I'm going to have an additional factor for c over the quantity x plus 1 squared. My strategy is going to be exactly the same as it was just plus x. I'll still multiply both sides, everything by the quantity x plus 1 squared. So we'll be left with a times x plus 1 squared plus b times x plus 1 plus c times x. And again, I could distribute if I want and write a system of 3 variables. But because there are values that'll make the quantity x plus 1 0, like x being negative 1, that's going to cancel pieces out. I might as well take an easier route. So I'll get 0a plus 0b minus c is equal to, and then on the right-hand side, I'm going to have 5 minus 26. So negative c is equal to negative 9, and c equal positive. Another one that's going to cancel out factors would be if x is 0. Then I'll get 1a plus 0b plus 0c is equal to 6. So a is equal to 6. Now, here's the problem though. I have no other numbers but I've never eliminated A and C and been left with B. So I'm just going to pick another easy value, like 1. But any value is going to work as long as it's not -1 or 0. When I plug in 1, I get 2A plus 2B plus C is equal to 31 on the other side. Well, I know A is 6, so 2A is going to be 12. I don't know B yet, and C is 9. I can use the two values I have already to help me find 2B equal to 10 and B equal to 5. Again, this strategy doesn't always work, but it's nice to plug in to evaluate rather than solve a big system, because there's less room for error. Does that mean I couldn't solve the system? No, I could do that as well. Okay, all right, next one. So here we have another partial fraction, but now I have in my denominator x and then x squared plus 4. X squared plus 4 cannot be reduced any further, so I have a quadratic denominator. For that quadratic denominator, okay, so I have a distinct linear and quadratic factor. So what I'm going to do now is I'll have a over x for that linear factor, okay, that has a constant numerator. My quadratic denominator, though, is going to have a linear numerator, so I'll have bx plus c. Now I'll do the same thing. I'll multiply by the quantity x squared plus 4. And I'm going to have ax squared plus 4 plus x times bx plus c equal to 3x squared plus 4x plus 4. Now the dilemma here is there is no real number that will eliminate x squared plus 4. So instead, this time I'm going to distribute. I'll have ax squared plus 4a plus bx squared plus cx is equal to 3x squared plus 4x plus 4. Now, when I identify on this, pieces that have x squared on the left, I have ax squared plus bx squared. That has to equal 3x squared. A similar equation that would go along with that is a plus b has to equal 3. Now the next piece I have is cx and 4x. There's no other pieces that are a constant on the left-hand side. So now I can just say c is equal to 4. And then I have one last piece, and that's my constant. And I have 4a is equal to 4. So from that, I can write the equation 4a is equal to 4. So we solve that one for a is 1. Then 1 plus b has to be 3, therefore b is 2. And now I can write my partial fraction. 1 over x plus 2x plus 4 over the quantity x squared plus 4. One last case, and that's repeated quadratic. So here my denominator would factor to x squared plus 2 quantity squared. So again, like on the last one, we have quadratic pieces. So my quadratic pieces are going to have linear numerators, okay? And we're going to have two sets of them. One for ax plus b over x squared plus 2, but then we'll have another cx plus d over x squared plus 2 quantity squared. So again, I'm going to multiply top and bottom, both sides rather, by x squared plus 2 quantity squared. I'll end up with ax plus b times x squared plus 2 plus cx plus d equal to 8x cubed plus 13x. I'm going to FOIL the first piece here on the left. I'll have ax cubed plus bx squared plus 2ax plus 2b plus cx plus d is equal to 8x cubed plus 13x. In each of these pieces now, I have cubed and cubed. I have squared and no squared. Squared is going to be to the, I have 0x squared. Ax and cx is 13. And then constants is equal to 0 on the other side again. So when I write my equations, I end up with a is equal to 8, b is equal to 0, 2a plus c is equal to 13, and d is equal, well, 2b plus b is equal to 0. Since b is equal to 0, you end up with 0 plus d is 0, d is still 0. Now, since a is 8, we're going to have 16 plus c is equal to 13. And then I'll move that over and get c is equal to negative 3. So what I end up with is 8x over x squared plus 2 minus 3x over x squared plus 2 quantity squared. And that concludes the 4 cases for partial fractions. Notice on all of these problems, the power on the numerator is smaller than the power on the denominator. That has not been a coincidence. Okay, on all of our examples we've done, we've had a smaller degree on the top than the bottom. We'll talk in class about what to do when the degree is the same or larger. This concludes partial fractions review.